Okay. Hope this is gonna end up being visible. Okay, so you got this graph here. So just bear with me here with the review. If you already did it, great, good job. Just make sure your answers are correct, I guess. So some notation stuff. When you see this little plus sign, that just means from the right. When you see the little minus sign, that means from the left. Okay, that's always a point of confusion. So in terms of remembering what that means, I don't know. I like to think of it as think of a number line. Think of 0 living on a number line. And where are the numbers that are plus, bigger than 0? Well, on the right-hand side. So as you approach 0 from the right, that looks like x approaches 0 from the right. If you're approaching 0 from the left, that's x approaching 0. So any questions on just that notation of left versus right? Looking at this graph then, as we're approaching 0 from the right, what are the f of x values approaching? What's the answer? 2. So the answer to this one is 2. Because imagine here's another point of confusion. So in pre-calculus right now, for example, people get confused on end behavior. And one of the reasons people get confused on end behavior is they start off mentally in the middle of the graph. And so there's an asymptote. I think in their mind, they're traveling to the right and shooting off into outer space. But you want to, for end behavior, you want to start off on the right. So for behavior like this around 0, I don't care about anything else except for this little region right here. I can ignore everything else. And I can just say, if I was on the graph and my x values were getting really close to 0, as I was coming at 0 from the right side, you can see my y values are all pretty close to 2. In fact, in this one, it's true that I could write that f of 0 actually is 2 because the dot is solid there. How about approaching 0 from the left? The answer to that is 1. That's okay. No, let's really make sure we are thorough on this one, because I want to field this question as few times as possible. But wait a second, there's an open circle there. Yes, so f of 0 is not 1. Okay, if you actually plug in 0 into this function, the y value is 2. But for a limit, it's just as the x values approach 0, but never quite get there. So we'd be talking about, in this case, x values like negative 0.01. negative 0.001, and so on and so forth. I do not care in any way, shape, or form what happens when x actually is 0. So is there any clarification on that needed? Good with that? Okay, sweet. Okay, so now what's the limit as x approaches 0 then? Does not exist, or undefined is technically fine, I think, but usually we'd say the limit does not exist, just like Mean Girls, our favorite movie. Right?
Oh yeah.
Lindsay Lohan, the hero of that film, determines. Huh?
She's the hero of all the celebrities.
She is? I don't know, it's just a great movie. It's a great movie about a girl's journey to determine that a limit doesn't exist. It's a good one, worth watching for sure. Okay, f of 0, as we said earlier, that's asking what is the actual y value. So since there's a solid dot there, it's 2. So this little packet of information right there, that little set of 4 statements, yes. Oh, so let me write something. Let's get here, I'll give you 2 answers. First answer is, that's the interpretive dance answer. For a limit to exist, what it means for the limit to exist means that the right limit and the left limit are the same. So I'll write anyone really, I know you guys live for mathematical rigor, so I'll give you the rigorous statement here, which is that I'll just use zero. No, I'll generalize it. So the limit of a function as x approaches, say, some number c can just be any number, exists if and only if the limit from the right is equal to the limit from the left. So if you want a really precise statement, it's this limit only exists if these are the same. So if the right limit, like in this case, if the right limit's 2 and the left limit's 1, well, they're not equal, so therefore the limit doesn't exist. What's the other way a limit cannot exist? Anyone? Yeah, so a limit is usually a number. So if the function's approaching infinity or negative infinity, then those are numbers, the limit doesn't exist there. So it's something like a vertical asymptote, the limit won't exist. Those are the two ways that we pretty much know where the limit. There's other kind of wacky ways if you're wondering, if anyone's curious. I think I might have shown this to you last year. There's a pretty famous function. This is outside the scope of this class, but the topologist sine curve, sine of 1 over x. The limit as you approach 0 for this does not exist. And the reason is, I won't talk too long about this, but if you try to approach 0, you end up oscillating up and down infinitely many times as you approach 0, and so you never quite approach a singular value. So that's the other way a limit can fail to exist, is if you just aren't approaching a single value. It's what?
So yeah, that graph makes sense.
Well, so if I try to zoom into it, it just looks like that. And that's because as x gets small, this value gets very large and thus spans a broad span of values. And think about how the sine function works. Sine function does this as the argument and as the inside of here increases. So that this thing starts increasing really fast, and so the sine function oscillates super fast. A really simple example is this one, though. This graph. There's some calculus for you. Oh, wow. For small x values, the sine graph looks an awful lot like y equals x. Oh, there's some high-level calculus there, actually. No, I'm being serious. It's real. You talk about a Taylor approximation of the function around 0. So, but as you zoom out, does this thing have a limit? For example, as x approaches infinity, what do you think the limit is of the sine graph?
Y.
It doesn't exist.
Yeah.
It doesn't approach a single value. It just goes up and down and up and down and up and down forever. So, okay, where were we? So, how about the limit as we approach 3? Nope. 4.
It is.
So the limit. So again, we go, wait a second. But if you actually plug in 3 into this function, the graph tells me that the y value is 1. That's definitely good information, but that just means that f of 3 is 1. The limit is what happens as x approaches 3, but never quite gets there. So numbers like 3.01, 2.99. You can see that from both sides we're approaching the same y value of 4.
Yeah.
How about as x approaches -2? Does not exist. This vertical asymptote there. And then f of -2. Now this is where it's not like that, and the vocabulary is not super critical, but we typically say, because in this region of the graph, it's probably generated by some kind of term like this. And so when you plug in -2, the y value is actually undefined because division by 0 is undefined. So just I guess take a word for it. Typically, people say undefined when talking about an x value that has no y value, and they say does not exist for a limit that fails to exist. I know, exactly. It's like that Office episode where Kevin just why use many words?
Why use many words when small words be tricked?
Yep, exactly. This says as x approaches infinity. What is the other name for this? Like, what's the simpler term?
When x gets big.
That's true. When x gets big.
End behavior.
Dylan said it. And George, thank you. End behavior. So this is just literally asking for the right end behavior. What is this graph suggesting? Okay. So this says basically as x gets very large for very big x values, what is happening to the function? It's approaching 0. Okay, now. Huh? Okay. List the x values of all discontinuities. So let's maybe go left to right. So starting over here, seems pretty continuous, right? Continuous, continuous, continuous. I see my first discontinuity at -2. There's a vertical asymptote there, so that's discontinuous. The simplest way, discontinuity, there's a bunch of rigorous definitions. Those are beyond the scope of like Calc 1 class, but the simple example is, where are spots on the graph where you have to pick up your pencil if you're drawing the graph? Okay, so like right here, you have to pick up your pencil to over here. And then we're over here. Oh, we have to pick up our pencil. There's a little gap in the function. So there we go at 0. And we can get a rigorous like definition of continuity. It just wouldn't be like there's different, I guess, levels of rigor. But anyway, we'll get to that later. So and then here's 1 at 3. I'd have to pick up my pencil to like draw that dot and then come back to finish the curve. So 3. So true or false? True or false statement here. At a discontinuous point on the graph, at a discontinuity, the limit can't exist. True or false? False. Right there. The limit exists there, but it's discontinuous. Okay. So, in fact, let's actually put up let's put a, just for now, we'll come back to it later. To be continuous, let's say at some x value, x is some value c, the limit has to exist. That has to exist, so it has to be, you can't be doing this, you can't be doing this, you can't be doing this. You gotta be doing this. And also, the y value has to be the same there. So this guy is not continuous. The limit exists, but the y value of the function is not equal to the limit. So to be continuous, like say, for example, here, it's continuous there because the limit exists, and the y value is also equal to that limit. Just put this back here. Okay. Hopefully that's sufficient review. 2 can be done on your own. I want to do a couple algebraically.
Take the algebra from
Wow. Epic prank. Okay, so taking a quick look at the first few here, does anyone either, maybe you just recall this, or maybe you can see it now. What type of graphical structure ties very closely in with these kind of limits? Does anyone know the answer to that? Holds. That's the answer. Yes, holds.
Good, right?
So I'll show you on A. Well, okay, doing any limit. Let's get this out of the way first. I don't like to put these on the problem set because I just find them to be like, they're so easy and simple that they're just kind of like a waste of time. But they do exist. I mean, you could see something like this. What's the limit as x approaches 3 of the function x squared plus 1? What's the answer to that? 10. That's it. So if the function that you're taking the limit of is continuous at that x value, then it's as simple as just plugging in the value. So your first step on limits is always, is it one of those dumb, like, just plug it in ones? Those ones aren't that interesting, though. The interesting ones are more like this. How do I know it's an interesting one? Well, I don't know that yet, but exactly. So I plug the 3 in. I do a quick test to see if I plug the 3 in, what happens? I get 0 divided by 0, right? That's intriguing, right? Oh, 0 divided by 0, what's that? In this case, it's 1. In this case, it's 6. It is. The answer is 6. So let's see, why is it 6? Well, once you have this established, this is called, if you're wondering, this is called an indeterminate form. Like we haven't determined it yet. That is, I don't know if etymologically that's correct. Indeterminate just meaning like, okay, we're not sure yet. Okay, what we do is we say that is equal to the limit. I don't know how many of you guys are planning to take the AP exam, but if you are, I mean, it's good to know either way. It's not just the AP exam. I'll clarify in a second. This is the next correct step, is to factor the top. You can cancel out the bottom. And now you say, well, what happens if I plug in 3 now? What do I get? 6. So the answer is 6. What I was saying about the AP exam a second ago is this. A lot of people do this. So just let the record show that I'm telling you, this is wrong. That is incorrect. That is a false statement, okay? So if you get to university and you do that, then you didn't know me. So why is that wrong? Well, this is a limit. This is describing a limit, some number, right? This is like an expression. So those are not the same thing. Those are not even, what you got to do, so just to reiterate, you need to say the limit of this is equal to the limit of blah as you simplify, okay? Oops, what happened there? What happened? Okay, let's look at B. First thing we do, very quickly plug in 4 mentally. Okay, we got 0 over 0. And then we factor. So this is equal to the limit as x approaches 4 of x minus 4 over x minus 4 times x plus 4. These cancel out. What's left over on top after you cancel that out?
1.
Yeah. Technically, that's times 1, if that helps you out. There you go. So now what we're left over with is, what's the limit as x approaches 4 of 1 over x plus 4? The answer is an eighth. 1/8. Can I confirm my answers with a machine?
Yes.
Yes, I can. I will show you. There's Desmos. This is a good way to do it. So if I type into the computer x minus 4 over x squared minus 16, and then I say, by the way, if I call this f of x, and I type in f of 4, what's going to happen? He's going to say, bruh. I don't know what that is, undefined.
Wow, the machine.
What if I plug in 3.99999? I get this number. That's awfully close to an eighth. Same if I plug in 4.0001. Okay. So if you're really lost in the weeds on a problem, it's pretty straightforward just to analyze it graphically. You can also do it this way. Limit of x minus 4 over x squared minus 16 as x approaches 4. Mr. Wolfram Alpha usually can interpret what you're saying. He knows the answer. It's 1a. Okay, so you can check your answer. It's pretty straightforward to check your answer, know if you're doing them correctly. I think you're better off just comparing with a classmate and maybe just discussing it briefly, see how you got your answer. Okay, I want to find, oh, here's a good one. Let's look at F. Who thinks they know the answer to this question? Okay, Dylan knows it. Keep thinking. Who knows the answer? Okay, Winslow thinks he knows. Ray thinks he knows. That's good. Keep thinking. My hint to you is think of that first step we were talking about. Every limit you do, there's a first step.
Oh.
Can we see it? What does that first step generate for us? 12 divided by 0. That is not indeterminate. That's not like a mysterious thing. What kind of structure would be existing on this graph at 6? Vertical asymptote. So this limit does not exist. How do we feel about that? So in terms of like a rule, if you're a rule follower, it's if you plug in a number and you get a non-zero number divided by 0, then limit doesn't exist. There's no way around it. The only time you're looking to factor and do that kind of stuff is when it's 0 over 0, indeterminate form. So you guys feel okay about that? Okay, so knock out that graph problem, and then like this is gonna be a very quick problem set. We're not gonna spend very much time on this. So if you're feeling like I really am like not getting it, let's just talk right now. I'll be glad to discuss it with you. And just again, another clarification, last clarification. What do you do when x is approaching infinity? What are you thinking about? End behavior. So when you see this, what's the limit of 100 divided by x as x gets arbitrarily large? What's the answer to this question? 0. You can think of it numerically, as in, oh, if x was 100 gajillion, well, 100 divided by that huge number is going to be awfully close to 0. But I would recommend.
Is a gajillion an actual number?
Don't think so, no. Good. It could be. You could write a math paper where there's some interesting number that is like central to the idea you're talking about and name it a gajillion.
Okay, but like how high did the names of numbers go? You know?
Well, there's some numbers that are interesting, like Graham's number is a number of interest that has a name, and that number is really big. There's a Google, which is I think 100 to the 100, or is it 10 to the 100? I think it's 10 to the 100. It would be a 1 with 100 zeros. It's called a Google, hence that's where Google got its name from. And there's a Googleplex, which might be that to the 100th or something like that, or it might be a 1. Yeah, I think actually a Googleplex is maybe that. 10 to that power. So a 1 with a Google numbers, Google zeros. But in theory, you could just go on and on, I think. But yeah, there's certain numbers. There's two really interesting ones you could look up are Graham's number and then tree 3. Tree 3 is a really cool one. So there's a very simple definition. It's like a function, the tree function. Tree 1 is like, I think it's 1, and then tree 2 might be 2, and then tree 3 is like just an astronomically large number. It has to do with like coloring graphs. Like you have some like graph with like nodes, and it's like how many ways can you generate the graph with coloring them in certain ways or something. You show how just
Some guy had too much time on his hands.
it's kind of a peculiar set of rules. So anyway, stream's over. So that covers all the material.
Streams over.
Oh, I don't understand how
Next
that
to the
one is
bed.
zero.